Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, welcome everybody. I'm happy to introduce Ivan Beshastnik, who recently graduated from UW, and will be starting as a assistant professor at UBC up in Vancouver, and he'll talk about his work in software engineering, and particularly how to understand complex logs from distributed systems. All right.
Cool. Thanks, Peter. Hi, everybody. So today I'll be telling you about my basically dissertation work, and the perspective that you should have in this work is that what I'm attempting to do is the following. Take the log, like the one you're seeing on the left, and attempting to convert it into a model, more abstract model, like this thing on the right. And the idea is that you can use this model for various other tasks once you've done this conversion. So the kind of the high-level view, though, for this is that I've started in systems. I've been building large systems, some of them distributed, and I've been always running into this problem, right, which a lot of people face, which is that you build a system and then somehow it behaves in an unexpected way. It does something that you would not expect it to do. And so the question is, how do you answer this question? And typically the setting here is that you have written some code, and perhaps lots of code, and you've looked at it, and you've attempted to test it, but you still have this question. And of course, there's some developer, some confused developer. And this developer has a mental model of what the code is supposed to do, right? So she's thinking about the code. She wrote down the code. And the reason this question comes up is that there's some disconnect, right? There's some mismatch between the mental model the developer has of their artifact and then the actual artifact, the implementation. So one typical way to kind of try to bridge these two is to instrument the system, run it, get a bunch of runtime observations of behavior of the system. So you would output this log, and then you would inspect this log and try to find out, OK, there's some lines in this log that somehow, when mapped to my mental model, give me some kind of contradiction, right? They create, maybe there's a loop on that invalid state, and that loop, I have never thought about a loop, but it actually exists in the implementation. And so the idea here is that you would generate this log, inspect it, and then check it for validity against your mental model. And this sounds really plausible, except that in practice, your systems are going to have huge logs. So your logs might be gigabytes long. They might be very elaborate. And as a developer faced with this very large log, you're not really sure where to look within the log or what to look for. All right, so the problem is that the log gives you a very concrete view of the system. And it's very easy to get a very large log, right? I just record all the methods I call. I just record all the activity. It's very easy to get a lot of information. The problem is to actually inspect it. So and then in a distributed setting, things get worse, right? The problem is that now you have multiple hosts, processes, and you have to reconstruct a distributed execution where you've captured logs for the different entities in your system, and somehow you have to string them all together. So going back to this kind of setting, what I'm going to tell you about today is an attempt to actually replace the log with something a little bit more abstract. So you want to not deal with the log, but deal with something that matches your mental model more closely, right? And the idea is that if you provide the developer with a model that models the log, a different representation, if you will, that's closer to their mental model, then it would be very much easier for the developer to actually inspect this model and find the disconnect, find where their mental model differs from the implementation. So that's kind of the context for the work. And this process of going from a log to a model is typically referred to as model inference. At least that's what I'm going to refer to it as. And lots of great use cases for this. So I've told you about mental model validation. But you could also use this for test case generation. So for example, you generate the model from this log. And if your model generalizes, then you can predict behaviors that are plausible for your system. And then you can use those behaviors to actually induce executions in the system. You could also use it to evaluate test suites. So you might say, I tested my system in this one environment, and then I deploy it in production. So its behavior in the test environment is going to differ from production behavior. And so how do I compare that behavior? How do I know what's present in production that's not present during testing? And so one way to do that is to generate the two different models and then compare them. Right? We know how to compare models in different ways. And you could find paths that are in production that are not in testing that should be exercised. You could also use it for anomaly detection. This is kind of the classic case where you take the model from last week, and then you take the model from today, and then you compare the two. So a bunch of numerous applications that you could use this for. In my case, it's going to be mostly about mental model validation. And so I'm not the first person to work on this topic. Prior people have worked on this in the software engineering domain, and they refer to this as specification mining or process discovery. And usually the name here depends on the task that you're going to use, that you're going to apply to the model. And prior work spans at least a decade of research. And a lot of the challenges that remain in this prior work are things like efficiency, accuracy, and distribution. And those are the ones that I'm going to sort of talk about in my work today. So the first one is efficiency. How do you get this process, this model inference process, to work on very large logs? Right? So it's OK. A lot of the prior work works fine if you have 100, this log is 100 lines long or 200 lines long. How do you get it to work on a gigabyte log? How do you make this model more accurate? What notion of accuracy can you use? And then finally, how do you get it to work for a distributed system, distributed setting? And so the three tools that I built are Synoptic, Denoptic, and invariant. And to briefly overview them, the contributions of Synoptic is it gains efficiency through the process of refinement. And I'll go into more details about what that means. It gains accuracy by mining certain properties from this log and then making sure that those properties are going to be true in the final model. And then Denoptic is sort of a follow-on work on Synoptic, which infers a different kind of model. So the model I'm going to attempt to infer here is one where I have a finite state machine per process. So Synoptic infers a finite state machine-like model. And in the Denoptic case, I actually want to model my distributed system as a set of finite state machines. And in Denoptic, it's going to apply some of the same aspects as Synoptic, like refinement and mining properties. But also, it's going to handle distribution. And then the final work is invariant, which is sort of very different from the top two. And I'm not going to talk about it much in this talk. But it fits into this puzzle in that it takes the idea of mining properties and composing them to the extreme, essentially, where there is no refinement in environment, where it just mines a set of properties here and then composes them in an interesting way. So this is really the motivation for my talk. And next, I'll really tell you about Synoptic and Denoptic. So there's not going to be any environment in the talk. So jumping into Synoptic. So the goal is you have this log, and you want to produce this model. And the way Synoptic is going to do this, initially I didn't tell you about any constraints on the log. So the first step is going to be just to parse this log. So I'm going to assume that the user will give me a log and a set of regular expressions that will match the lines that they care about in the log. So if you care about disk in your system, then you give me regular expressions to extract disk events. And then I'll build you a model that's relevant to just those sets of events. The second step is to then build a compact model. You want to build a model that will include as many behaviors as possible. So it'll include the behaviors that you have in the log, but then many more things. And then what we're going to do is mine these properties, or what I call log invariants. And they're going to be very temporal-like things, like lock is always followed by unlock, open always precedes read, and then use these invariants to constrain the model. So I'm going to take this initial model, use the invariants that I mined, and then build you a more accurate model. Yeah, Gabby.
Expressions. Does you have to specify just this is related to disk, or it also has to specify these are the disk states and these are the disk transition events?
Right. I'll give you. Yeah, I'll give you an example of what I mean by regular expressions. But overall, I think of this log as a set of events. So I do not reason about state at all. And so the model I'm going to give you, actually, is going to be an event-based model. So I'm modeling sequences of events. And so your regular expressions basically have to tell me, for every log line that you care about, associate an abstract event with that log line. So if you're sending a message, like it might be an acknowledgement message, an acknowledgement backend in TCP, it has a sequence number, it has all sorts of stuff in it, but your abstract event type is acknowledgement, right? That would make sense if you're attempting to come up with a model that reasons just about the event types. And depending on the setting, you might say that's unreasonable, right? So you might say, OK, maybe I care about every 5th acknowledgement packet. So it would be acknowledgement 5, acknowledgement 10. Right. So this. Right. So you would include that into your regular expressions. But in general, this does not reason about data. So it's not powerful enough to reason about data and state.
If you have this acknowledgement model, right? If I want to model a handshake, then I have to give all the thing, like starting up, setup, and all these events?
Yeah, you would. I mean, the answer here depends on what the log looks like, right? So if your log is in a certain format, then you can just say you have a regular expression that matches different kinds of events and extracts some subset. Let me work through these different steps. And actually, I'll go through them in order. And the example that I'll use is kind of a very simplified version of two-phase commit. So in two-phase commit, you have a manager, and you have some number of replicas. And the manager is going to propose a transaction. And then your replicas will reply with either commit or abort. And then the manager will say, OK, collect all this information, and then either reply with transaction commit if I've seen only commits, or reply with transaction abort if there's one abort or more. So the way we're going to cheat here and use Synoptic is that we're going to maintain a totally ordered log at the manager. So we're not going to care about logs anywhere else because I can have a total ordered view, global view at the manager. And that's the log I'll plug into Synoptic. So in this case, my input might be these sets of events. And then my regular expressions are going to extract just the packet types or event types that I care about. And for two-phase commit, the things you care about are what kind of messages are you sending? Propose, abort, transaction abort, commit, so forth. So I'm going to essentially extract these execution chains from this log. One thing that I should mention is that you also need to have something that tells you basically tells you execution boundaries. So in this case, the transaction ID is going to be your execution boundary. So every new transaction will induce a new execution. And the kind of the format I'm using here is that the square node is going to be this initial node. So all of the proposed nodes, the first ones, are going to be the first ones. And then the very bottommost node, the terminal node, is going to be this rhombus. So I have this initial set of traces. There's going to be a huge number of them. And what I want to do next is build this compact model. So the compact model is going to be built very simply where I want one node, one abstract node, for every kind of event that I have. So I take all of the, for example, I might take all of the proposed nodes and create one single proposed node to represent all of them. And I'll take all of the commit nodes and create one commit node to represent all of them. And I'll do this for all the event types that I have. And then I'll create edges between these based on the concrete observations. So if there's a concrete edge between commit and transaction commit, then there's going to be an abstract edge between the commit in the abstract model and the transaction commit in the abstract model. So basically, I just built you a model that's very compact. Compact in the sense that there's only one node per event type. And it admits all the behaviors that I observed in the log by construction. Right? But this model also admits lots of other things. So now the question becomes, how do I get this model to be a little bit more accurate? And this is where invariants will come in, or there's log properties. So we build this compact model. Now we're going to mine these salient log invariants. And it turns out that you can get away from pretty complex systems with just very simple properties. Right? So for Synoptic, we're actually going to use just these three properties. They're going to be temporal properties. You can express them in LTL, but I'm not going to show that to you. But in general, we know from prior work by Dwyer et al., for example, that in general, when you specify systems, there are very few patterns that you tend to reuse. Right? And so these three actually cover the top 6 patterns out of 10 or so that Dwyer documented. And so the patterns here are going to be x always followed by y, and on the example log, x always followed by y would look like abort is always followed by transaction abort. So when you see an abort event, then you know that before the trace ends, you will see transaction abort. And commit always precedes transaction commit is kind of the reverse, looking back. So you look at transaction commit and that third trace, and looking back, you must have gone through a commit event. So this one really parallels causality. And then the final one is abort never followed by transaction commit, which basically is what you think it is. If I reach an abort event, then I will never see transaction commit in the same execution. Gabby?
So maybe I missed my most you build a model based on a log. You said you want it to be more accurate. It's the most accurate it could be. It captures exactly what happens. So this is accurate. What I'm trying to do now is come up with more compact model.
No, it's actually that initial model that I told you about, right? That construction. That model represents the log, but it also captures other things. So there are paths in that model that you have never observed that are illegal. And so it could happen because you're essentially stitching together executions. So here in this model, this edge might have come, abort always followed by transaction abort, might have come from here, right? But then the edge preceding it might have come from a different execution. And so you might get a path in there that actually composes two different executions, right? And this is really the power of this model in that it generalizes by stitching together different executions based on common events.
Models.
Well, now my question is, I have this model and it generalizes, right? How can I make it a little bit more accurate? And accuracy will come from these invariants. So these things that I told you about, what I'll do next is actually mine these invariants from the log. And then I'll tell you about a process for changing the model to satisfy these properties. So that, for example, this first one, abort always followed by transaction abort, if you actually mine this property from the log, right, you would like the property to be true of your model. That's also a kind of a generalizing statement. It says that there's a bunch of behaviors that we haven't seen of your system, right? But if we've seen this property for all the executions, then we would like this property to be true of the model, right? And this property is also a correctness requirement for two-phase commit, right? So you would like this to be true of the model as well. So
I'm sorry, so these are inferred?
These are going to be mined. Yeah, exactly. So I'll show you that in a sec. I have a note here about kind of related work. I mean, there's been a lot of work on actually inferring these temporal properties from sequences in different domains, and a lot in the software engineering domain. And I guess the contribution of this work is to actually use these properties for model inference, right? So they're not, I mean, you can see them in the tool, and I'll show you where you can see them, but that's not the purpose of the tool. So for two-phase commit, here are all the invariants you would mine, right? So this is the set of all of them. Some of them are going to be false positives because your log might not include all possible executions of your system. And some would be actually true of your system, right? And depending on how interested you are in inspecting these, you can deselect some of them, right, to have the model be not constrained by the false positive. No, these are mined automatically based on those templates, those three kinds of invariants. So now the question is, how do you combine these two? So you have this initial model, you have these properties, and you want to refine the model to satisfy the properties. And to give you an example, so for this initial model, right, the ones that I grayed out below, all of these properties are already true of this model. And what I mean by true or not true is that, for example, the top one, abort always followed by transaction abort, this property is not true of this model because there's a path in this model that violates this property. Right? So there's a path, propose abort, commit, transaction commit, where you go through the abort node, but then you don't reach the transaction abort. So that property is not true of the model. So those three are not satisfied. Now the question is, how can you satisfy it? And the answer is going to be essentially for each violation, right, for each of these counterexamples to the property, we're going to use counterexample guided abstraction refinement to eliminate it. And it's kind of a technical term. I'll show you how it works. So this initial model is what you start with, and then you have this invariant. And this invariant is mined from the log. So it's true of the log, but it's false in this current model, right? So the first step is to find the counterexample. So this counterexample is exactly the same path that I showed you in the previous slide. And you want to change the model to eliminate this counterexample. So the thing to realize about this model is that really it's a partition graph. So it's an abstraction of the underlying concrete events. So that commit node, this commit abstract node, contains a bunch of concrete instances of commit from the log, right? So you have this underlying graph structure induced on it. And so to refine a partition, or one way to change this graph is to refine this partition, right? So somehow we grouped all of these commit nodes, assuming that they're the same, right? But the realization is that actually they're not the same. And the way we're going to differentiate them is based on these properties. And so you can change this larger commit partition into these two partitions that are smaller, right? And by doing so, you actually eliminate that path. So now, when you kind of look at the more abstract version of this graph, when you reach the abort node, you have to go to the transaction abort, right? There's no way you can get to transaction commit. And so by doing this refinement, you've eliminated this counterexample, right? And you're going to do this over and over again, right? So you're going to eventually satisfy all of the properties that you mine from the log and get a more accurate model. And that's kind of the core of the Synoptic procedure. Yeah.
Because of the procedure, you're still guaranteed that all your original traces still parse through the graph.
That's right. The model will still always accept the logged executions.
So then the question becomes, like if you have a huge database, you probably have a large set of invariants that you mine, and now, depending on the order in which you address the invariants and all the counterexamples to each invariant, you have a huge search space with graph, the final graph that you might end up with.
That's perfect. You're leading right into my next slide. So the
Are you
more.
going to explain how you do the refinement? Are you going to explain how you do the refinement?
Well, the refinement is there's a set of heuristics that we use for refinement, because to eliminate the path, what we do is actually find the first node that you're stitching multiple executions along the counterexample. So the first partition where that happens. And then the way you break up the partition, I mean, it's a little bit detailed because there's kind of different sets of concrete events, right? There are events that are concrete events that are from these two different paths that you're stitching together that you should eliminate, right? So you should have them in two different partitions, right? And then everything else that's in that partition. And so the different strategies are make these partitions as balanced as possible and assign the remaining commit nodes there randomly, right? So there's actually different kinds of.
Just like you said, you look at the log as a set of regular expressions, and then you got into this problem. But actually, the log was not a set of unrelated regular expressions. It was a set of sequences, like a much stronger grammar, basically. Each execution was not a regular expression. It was actually
right. Yeah,
a sequence of them. So it was a program. You kind of forgot about that in the first stage, and now you're kind of regretting.
Yes.
Coming kind of back versus maybe that's what you should have done initially. Look at each execution, build a model, and then just say, okay, these are the same model, these are not.
Well, I guess the initial regular expression parsing is intended to abstract the log, right? So I don't care what. I lost some things, but the idea with the regular expression is that you compose them, right? So you get to choose what you lose and what you keep, right? So do you care about the disk or do you care about network, or do you care about both? Which events interest you, right? That is the concern that the user will have.
I think to rephrase the question, could you have, instead of, you treat each event individually, you just look at pairs of events? Well, you look at pairs of events when you create the initial model.
Right.
You look at sequences of 3.
Oh, but those are already.
Or maybe, so you.
But those are already satisfied, right? So in the model
Right, but then you're generalizing too much, right? If you maybe build a model.
But I'm generalizing as much as possible.
No,
right?
but then you have to fight it, and then you have to.
That's right. That's a good point. I should tell you. So let me move to this slide. Let me describe this. So here I worked out an example for you on a smaller log that has a bunch of these models, right? And so the model on the left is sort of the trace graph. This is what you would actually parse from the log, right? So these are the individual chains. And then the model on the right is kind of the initial model that you start with, where you have one kind of partition for every event, right? And so this is your span, right? The model over there is the most abstract one, and it's the most condensed one, right? So it admits a lot of behavior. The one here is very large because it's very concrete, and it admits only the things that you've seen, right? So now the question is, like, which model do you want? So this model is the log. So if you want to look at the gigabyte log, you can use this model. That model over there is very small, but it's going to admit a lot of stuff that you don't want.
So the point is, if I went from the huge log only by doing analysis, looking at compaction into the model, which
Right.
always preserves exactly that, I would still be in a huge model.
Well,
so there's a compromise.
so there have been other approaches that start with this and actually go this way, right? I guess the approach that I'm describing here is one where you start with that model and you go this way. The problem with starting from this direction, right, is that you're going to have to do a lot of compaction, right? What we found in general is that starting there is going to be way quicker. So performance actually results for our technique are way better than the versions of techniques where you do compaction, right? Because here where you actually have to there's one algorithm which is like k-tails, where you do compaction based on length of strings, right? And you find ones that have identical run, and then you compact them and you merge them, right? So that algorithm is going to be very inefficient on a very large graph, right? Whereas this thing is going to be much more efficient because you start with something much more compact. So that's really, there's a lot of trade-offs. So our algorithm is to basically say there's going to be this dividing line. And this dividing line separates models that satisfy all the invariants. And obviously, this one will satisfy all of them by definition. And then models that violate at least one invariant. Those are the ones in red. And so some invariant violated, all invariants satisfied, right? And then the exploration stage is going to be, well, and here's the model you actually want to find, right? You want to find a model that is as abstract and small as possible, right? But is in this green space, right? Because it satisfies these invariants. And you can change the definition of this space, right? You can add another kind of invariant, and this line will move to the left, right? Or you can remove an invariant, and the line will move to the right, right? And now the operation that you have is refinement, right? Refinement will start with some model that's further to the right, and will produce a number of models to the left, right? Depending on your heuristic, depending on which invariant you're going to refine, depending on which counterexample you want to eliminate, and so forth. And then other techniques use coarsening, right? So refinement is the thing I described. Coarsening here is going to be the technique from prior work, which is like k-tails, where you're going to merge nodes. So this one splits partitions, this one merges partitions. And you have these two things. Now the question is, how do you get to this intended goal model? And that's really the problem that Synoptic attempts to solve. And in practice, what this will look like is you start at this initial model, you have some number of choices, you're going to have to make a choice. And in practice, we found that there's a lot of strategies, but they're all suboptimal. Unfortunately, you're never going to get the global optimum here, right? And so we select something very simple and cheap as possible, because each of these partitions might have thousands of events. So choose some simple strategy for actually doing the splitting of nodes, and then keep going. So you end up at this model, you have some more refinement choices, and then once you jump over this line and end up in this in the model that satisfies all the invariants, then we're going to apply coarsening. And the idea with coarsening is that it's sort of like a local optimization, right? It's a local minima where you want to merge partitions locally, right? But it's not guaranteed to find a global minimum. So that's the full algorithm. And one note about prior work, this idea of starting from the far left and then going to the right, which is just using coarsening, has been explored in prior work, as far back as the 70s. But it's very inefficient, right? And so really the contribution here is to come up with refinement and also to use these invariants as a guide for what kind of refinement to actually perform. So that's kind of the synoptic technique. Now the evaluation, we've done a couple of different evaluations. One was to apply it to a system, reverse traceroute. Second one was to actually have students in a class use these. So the handwritten diagram that I showed you at the very beginning was by a student in a class they first had to kind of write down the model of their system and then run Synoptic on the system and then compare the two models. And then we've also done some formal evaluation to show that the algorithm always terminates, that it has these nice properties like always satisfying, always accepting the log, satisfying the properties, and so forth. So I'll only tell you about kind of this small user study with the developer of reverse traceroute. And so first to tell you, reverse traceroute is a system for actually finding the reverse routing path on the internet. So typically, you run traceroute to find the forward path, but the reverse path is usually obscure, and you don't see it. So the reverse traceroute is a system which uses multiple vantage points and a controller to find out what path your packets are taking on the reverse path. And deployed internally at Google, has been deploying for a while. And what we've done is apply Synoptic to the server logs. And so the developer had to change their logging code, which is not good. Ideally, you would like for this to apply to just existing logs. But they had to change the logging code to have better formatting. So it's too freeform, it's too difficult to write the regular expressions. And we've basically processed about 1 million events in 12 minutes. And the model that we got is the following thing. So unless you're a developer of reverse traceroute, this will not make a whole lot of sense to you. But basically, a single path in this model is a path that reverse traceroute takes as an algorithm, right? So sometimes you perform measurements, sometimes you assume symmetry because you don't have any measurements and so forth. So those were the key things that were logged by the developer. And each of these corresponds to a method in the code at the controller. And so I'm highlighting a couple of things. And one thing I should say is that there are numbers on these edges. And the numbers are actually probabilities. So, and they don't always sum up to 1 in this diagram because for this developer, this graph was more complicated. So we had to hide the low probability edges in this diagram for this to be more readable. So it's kind of, you could think of this model as, you could look at just common behavior, which is what we're showing, by hiding low probability edges. Or you could look at rare behavior, right, if you want to find rare occurring bugs, for example. And then you would only show the low probability edges, right? So you could have different use cases. So this one was showing the common behavior. And the things I'm highlighting are 2 issues that the developer found. One was these rhombus nodes that are shaded are terminal nodes, but they shouldn't have been terminal. So the system was essentially one execution of the system would terminate at an event that was not supposed to be the terminal event. And that was one thing that the developer found by looking at the model. And then the second thing are these dashed edges. So these dashed red edges were not present in the final model. And so, but they should have been. And so that was the other feature that the developer found.
So when you say that the shaded node should not be terminal, the developer just knew that, right? Or was that inferred by?
No, the developer knew that,
okay.
Right? So both of these features were found by the developer, right? So I basically overlaid on top kind of the developer's interpretation of what is a bug and what is not, right?
So you basically told me, there is an execution that violates what you think is correct, and you may be able to point, oh, like this happened in this line in the log, and here.
Yeah, so I'll show you the, so here's, let me actually show you the tool. I have it running online, and here it is. It's called Synoptic, and so so here's an example log, right? So this log is going to be an Apache log, where you have a bunch of GET requests to Apache, and so you have access log. And this log is going to be for a web application that's like a shopping cart, right? So people come online, they check out, they get a credit card, and so forth. So the input to the system is going to be this log, and then these 2 regular expressions. So the first regular expression, you'll note that it matches every log line. And so it matches this thing perfectly. There's some IP address, and then there's this get HTTP. And then there's this magic keyword type. And type is going to be our abstract event type, right? So the abstract event type is going to be just the name of the PHP file that you're getting. And then the other thing that you need is to actually somehow split these executions. So what is an execution boundary? And in this case, the execution boundary is simply the IP address, right? So a new client to the server is a new execution of the system. And so basically, you have executions that are matched 1-to-1 with the clients.
And what if you're handling clients concurrently?
Yeah, and that's here. You will actually notice that they're all intermixed. So it's going to actually pull them out. Yeah. So this is the only input to the system, and then the model that you'll get out will be something like this. I'm not a graphics person, so I couldn't make this like fantastically looking, but here it is. So basically, you start off in this initial node, and then a trace starts in initial, ends in terminal, and then goes through these partitions. And you can click on any one of these partitions, and then find out the log lines that are matched up, that are basically merged into that one partition, right? So there's some invalid nodes, and then there's 2 checkout nodes. So there were 2 checkout nodes that were differentiated based on the invariants, right? Because somehow they were considered different. Let me see if I can make this look a little bit better. Yeah, so the question for you guys then is, can you find a bug in this model?
Invalid coupons should not reduce the price.
Yeah, that's right. So that's kind of the idea, right? Do you guys see that? Right, so there's a path where the invalid coupon you would assume would take you back to checkout, for example, but it doesn't. It goes to reduced price. So, what does that mean? Well, it means that there is this transition is actually in the log, and you can select 2 of these partitions and say, what are the paths that go through these, and you'll find that there's some 15 traces that actually goes through both of these nodes, right? And then ideally you would jump back to the log and actually find those traces. I didn't build that thing yet, but that's the intuition for how you would use this model, right? It's an abstraction of what's in the log. The log has a lot more detail, right? It has timestamps, it has IPs, it has all this other stuff. But really, when you think about the logic of your program, maybe you don't care about any of that, right? What you care about is just the event sequence and whether it's reasonable.
How do you find those probabilities? Events.
How do you find the what?
Probabilities like 0.5, 1.
Yes. So the probabilities are based on the number of events, right? So initially, like this checkout node contains n events, right? And then n over 2 go to this guy, and then n over 2 go to this guy. So the probabilities are based on the concrete observed events.
So how do you say that? So is it like if checkout event happens? I mean one invalid coupon can. Checkout can cause many invalid coupons. I like that. So how do you say that this checkout is for this invalid coupon?
Yeah, so in the log, right, there were some traces that went this way, and then some traces went this way, right? And so exactly half of them took this edge, and then the other half took this other edge. And that's where the numbers came from. I didn't talk about them in the talk because you could show much more information on top of this model. And probabilities are just one thing that we thought about. I mean, the one other thing you could show is actually like time or a distribution of time, right? Because if you have time between events, then you can say, here's the shape of like the timestamps, for example. But it's based on the concrete underlying log. And it's added to the model after the fact. So it's not used in the actual model inference.
Just one question about this. These probabilities that you are deriving here, you're kind of assuming that the process where the log came from are completely like Markovian, right?
Yeah, you assume that it's a sequence of events. And that it's reasonable to model a sequence of events in this formalism, right? Yeah.
I don't understand the semantics of the probability because of so you have 2 branches going out from initial to checkout, one that goes to a get credit card and one that goes to coupon group, but they both have probability of 1.
You mean this one, right?
Yeah.
Yeah, that's actually a bug. I keep, it's sad. I keep presenting it over and over. People keep finding it. I have to actually go fix it.
More serious question.
Yeah.
So have you thought about, so there's this interplay between filtering the invariants and the complexity of the model that you generate, right? And at least as you presented it, was okay, we discover the invariants and we select which ones we're going to...
Well, we select all of them right now. So as a developer, right now, you don't, so in that screen, in that input screen, you don't get a choice. I mean, one thing I didn't tell you...
As an author of this algorithm, you have some threshold for the strength of the invariant.
Yeah, the invariants are all very simple right now. So they have to be true for all of the executions, right? So yes, if ideally, you would want like a probabilistic invariant that would be more robust. So you'd say 99% of the time this is true. Maybe the 1% of traces are actually just malformed.
And do you take all the invariants that are true all the time?
Yes, and we use all of them. Absolutely. Yeah. So and you could look at them here, right? So here are all the invariants that we mined for this thing, right? And here's a little visualization that you can sort of see. You know, always followed by, always precedes, and never followed by are red. And so you could take these and then actually remove them. And then the model would change, right? And so so this gives you some kind of knob to go and tweak. So if you disable all the invariants, then your model will be the initial model, right? You would perform no refinement. Yeah.
So is this what you do? I was wondering and worried about scalability. I mean, if you rely on a visual representation of a state machine, I mean, usually it doesn't scale more than 20, 50 nodes max or something like that.
Yeah.
So when that's the case, what do you recommend? Like simplifying, removing some of these things, or do you have, or use fancy visualization for very large things, or
Yeah.
graphical, or
when I started this project, I didn't think that visualization would be kind of an important component of it, and it turns out that it is. We found that in the regular, for example, in the traceroute model that I showed you, we had to remove nodes and edges of low probabilities in order to make that model kind of fit on the screen and be readable. So that was one simplification that we've done on top of it. I would actually argue that what you really want to do is choose a different smaller component, or choose a different abstraction for your model. So basically, to me, it means that the slice of abstraction that you selected with these regular expressions on top of the log is simply too close to the log, too concrete, right? So you should raise the level of abstraction in order to make that model be more easy to interpret. But that's not always the case. Sometimes you do have a lot of, it really is a complex state machine. So this tool, definitely would not work for a very complex system that has that complexity. Yeah.
So a question from Navenda who's watching online. He's asking whether the bugs you found in the reverse traceroute, how critical were they? Were they sort of no low impact because if they actually caused crashes or performance problems, they would have noticed them earlier?
Yeah.
Or if you have any sense on
Yeah, so the developer knew about one of them. Like they knew that this thing happened. They didn't fully understand where it came from. And actually, the model doesn't tell you where it comes from either, right? It's like a diagnosis tool. You then have to go and find the root cause after all. So the underlying cause was a threading problem, was a concurrency problem. The bugs were not, they didn't crash the system. So they were not severe. They were not that severe. Okay, so I'll switch over. So I showed you this demo thing. So to summarize, Synoptic takes this log from a single totally ordered log and produces this event-based model. And it does this with refinement and then leverages these mined invariants that it satisfies in the final model. And primarily, the use case here was comprehension. So the idea is that you want to help developers with large and complex log. That was the original intent. And it's open source and it's deployed on this web interface. Sort of scales. Yeah, please.
What's the largest log that you've run?
Yeah, like 1 million log lines.
Mm-hmm.
Yeah, that's as large as we've done.
So was it the reverse?
Yeah, different versions of reverse traceroute. We've done larger ones for it. The complexity of the algorithm really depends on the number of event types and the diversity of the log that you have. So the more connected your graph becomes, the more difficult it is to check those properties, to model check those properties. And then refinement, of course, slows down as you have more events. So the next project I'll talk to, yeah, please.
Did you do any investigation of how robust this is to the loss of log lines, or if you happen to log inside one branch of a condition but not the other, and that kind of thing?
Right. So it wouldn't pick things up that you haven't logged. So it's very much constrained by what you have in the log.
Suppose you were to just take out a single log line from a log, how badly could that screw up the model?
Right. It's a good question. If you have another execution that is just like this one, then wouldn't change the model, because you would essentially, you have this redundancy, right? You have underlying concrete executions would still have the same edges, and you would mine the same invariants. and refinement would perform, the same. But if you remove a log line that would remove an invariant, for example, then it might change the model radically. Gabby?
In the case, say, in one execution you have a event and the other it does not, then that will show as an error, right?
What do you mean?
So, say one execution has some logs omitted, and another execution there are some logs. So you will show it in the execution where the logs were omitted as an error.
As an error? It wouldn't, well, the model would present both executions, right? And it would merge those sections of it that it would be able to merge. But it wouldn't, it wouldn't show you an error, actually. It would attempt to satisfy both. It would attempt to model both.
But what if that violates certain invariants?
What about what?
Certain invariants, like...
So certain, yeah, so the invariants have to be true for every execution. So if there's at least one execution, even if you have 1 million of them, that doesn't satisfy the invariant, then you throw it out, right? Then you're not going to mine it, and then you're not going to use it for refinement.
Almost in the converse, where you have one trace that demonstrates what looks like an invariant because the precondition for the invariant only happened in that one trace. And if you had run 1 million more runs, maybe you would have found the case where you hit that precondition but go the other way, so it's not really an invariant.
Right. It would be a false positive.
Right. Yeah.
Absolutely, right. So yeah, you would mine the false positives along with the true ones. I mean, the answer here is really you want as much information as possible, right? For the model to be accurate, you need to observe more things. Okay.
So for when you build the initial model with just one linear scan on the log, just
right.
matching every line with your expression. Now when you do the refinement with invariants, does mean you need like a random access back into the log and so for that you basically to store it in memory, or how do you do it?
Yeah,
That's become the bottleneck for the...
Yeah, the memory pressure is definitely a bottleneck because
you need to store the whole log in memory?
You need to have the whole log in memory right now. There's some optimizations that you can make where you really need to store some concrete aspects of the traces, right? You don't need to store all of them. So for example, if you have 2 identical traces, I just need one of them. I don't need both, right? So that kind of is...
Right. From the left.
You're right. I would just compose them. And there are other cases where you might not need to store some things because they, during the merge, the invariants are satisfied, right? So if certain partitions are not going to be ever refined, so then you can lose them. Well, you can know that sometimes because the underlying refinement assumes that you can only refine a partition if it stitches multiple executions together, right? That have different features essentially, right? And that's when you're going to want to refine it. So the optimization would be, I take that partition and then I check if I can check that all the invariants are satisfied below, then I can throw away the state for that partition. That would be one optimization. But yeah, we haven't implemented any of those. So that would be kind of future work. Yeah, I think, I mean, you definitely, this is a single-threaded Java process right now. So this is not optimized at all. It's mostly experimental. So let me jump into this Synoptic thing, because it has a bunch of details that you guys might or might not enjoy. So the sequential case was you have this, the intuitive model there is kind of a sequence of events. The question is, what is intuitive in a distributed case? And in a distributed case, when we told students to write down a model of their system, they came back with pictures that looked like this. Right? So basically, they would model each component as a finite state machine. Right? You would model the client finite state machine. You have the server finite state machine. And the only catch is that the server emits events that the client consumes. Right? So they're actually linked. And so this is very intuitive to students. And the idea was that, well, people are familiar with finite state machines. So let's use a formalism that's close to this. So in the Synoptic case, you would infer an event-based model. In the Synoptic case, we would actually infer a model that is a communicating FSM, communicating finite state machine. And let me tell you more about what these things are. So CFSMs basically have some number of processes, and they're connected with FIFO queues that are reliable. So one example FSM, CFSM that I'll use here is a very simple one, where you have process 1 on the left, process 2 on the right, and you actually have states, and they both start off in their initial states, and then you have these funny-looking transitions where some of them may be communication events. So exclamation M means that you want to send M on Q1, so sort of enqueue M into that queue. And then question mark M means receive that M on that queue. So, and once you receive it, you can proceed, right? But you cannot execute this event unless there's actually an M at the head of the queue, right? So this is really modeling message passing. And if it also includes local events, so you can execute a local event for free, right? And then you might communicate back over a different queue, because the queues are unidirectional. And then you would consume it on this end, and that would be a complete execution. Yeah.
Using queue in just the most abstract sense. So just a way to get data from one point to another.
Exactly.
So that could be anything.
Yes. I'm not assuming anything. This could be shared memory. This could be a socket, right? Yeah, so this is one execution of this CFSM. There's only one execution of the CFSM. But in general, they may be asynchronous, right? Because there might be another process that I'm communicating with independently, right? And they don't have to match up. So the idea here now is, what if we have a log and we want to produce this kind of model, right? How would we infer this kind of model from a set of events from the log? So, Synoptic, very similar sounding to Synoptic. So our pipeline is going to resemble Synoptic. We're going to have very similar steps where we parse the log, build this compact model, mine some properties. These properties are going to be more interesting because now they're going to be events at certain processes. So I might have something like send at process 1 is always followed by receive at process 2. And then I'm going to use something like refinement to get the final model. So very similar. And so I'll describe all of these steps kind of now in the Synoptic setting. So the first question is, OK, so you have a log. How do you get back an execution out of it? How do you parse it? Well, it's a distributed log. So what you're going to need is something like vector timestamps, right? So you want to actually capture the total order, the partial order of your system execution. So these vector timestamps are logical clocks that you can use to reconstruct the DAG, the partial order of the execution as it occurred. And what we have built is like a little library that you can compile. It's for Java. You compile your Java, recompile it with this jar, and then existing logged messages would then have these vector clocks put in automatically, right? So you get this logging for free. So you don't have to have it part of your system. We'll add it in automatically. It's going to have an overhead, but you don't have to worry about generating these timestamps.
You said that you would add the vector clocks into the log?
Yes. So assume that your initial log was, so like if you didn't have these things initially, right? You just had the thing on the right. So then you compile it with a jar, and it automatically tracks, sends and receives, and tracks causality, and then just adds these to every log line. So when you log normally, you get Q exclamation M, but then it would also prefix this vector clock. So the idea is that you just want to capture the partial order, right? And I don't want to change your log because you log some things for a reason, right? You just keep that. But I want to keep the causality. I want to reconstruct it. So very basic vector clock mechanism. OK, so you have this log now. So how do we build the initial model? It's going to have kind of two steps. So first of all, we're going to deal with state. Unfortunately, because these CFSMs have queues, you actually have to reason about message FIFO state. What messages are outstanding. So first, we're going to reconstruct the state. And then we're going to do partitioning, not based on events, but based on kind of queue state. So let me show you how this looks. So initially, you have this time space DAG that you parse from the log. And then you want to come up with a state-based DAG. And the process here is going to be very simple. It's going to be simulation, where I first see the first event. Well, so I start off with a state where both of the queues have no messages. They're empty. Then I see the first event. It's a send of M. And so my simulation will basically say, OK, I just want to add M to that queue. Then I receive it. Then I go to a new state that has both queues empty. I execute a local event, doesn't change the queues. And then I execute the ACK kind of sequence. So the idea is that you would parse a bunch of these from your DAG. And now you have a model that has states and events. More complicated than Synoptic, but you can apply some of the same ideas. And so the idea now is you want to build this initial global model that is compaction. And remember, in Synoptic, what we've done is we've seen commit and commit, and we've merged them together. We assume they're the same. In this case, we're going to build a state-based version of that. So we're going to look at these queues, and then we're going to merge queues that are the same. And actually, in practice, there's going to be approximation here, where we're going to merge queues that have the same top k messages. Right? So we're just going to assume that after k, the queues are identical. Right? So this is where we're going to lose our this is where it's not going to be exact. So Q1 and Q2 is going to be this abstract state that represents all of these orange states. And I'll do the same thing for this guy and the same thing for this guy. So now I have all of my abstract states, and I create arrows between them in the same way. So I have a transition between a state where I have an M and the state where all queues are empty on receive M, if this actually happened in practice, right? If I saw the concrete event that made this transformation. So now I have this initial global model. It has some of the same great features as Synoptic, right? So it accepts the log, where every one of these executions in the log is going to be a valid trace in this model. But this model is actually, you can think of it like a cross product of the process models, right? It's not actually a CFSM. You have to reason about global state, global events of all of your nodes. So the actual decomposition is going to come up in refinement. But let me tell you about invariants. So invariants are going to be very straightforward, right? You have a bunch of these DAGs, and what you're going to do is mine the same kinds of events, the same kinds of templates that we had in Synoptic, except that now your events have kind of a process ID associated with them, right? So you might have an event that only executes at process 1, is always followed by an event that executes at process 2. So you mine the same set of things. And now the question is, how do you use both the initial model and invariants to get this CFSM formalism that I told you about before?
Invariant there, like a message M is sent on Q1 and then received. It's always enforced by construction, by your logging. No? Am I missing something here?
That one, yeah, I think you're right. It is enforced by construction in the logging. Yes. So but it's not enforced by model. So you still have to. I haven't thought of that. That's actually a really great point. So you don't have to mine it in a sense. Yeah. So you can just add those. The reason it's actually there is because the library that adds the vector timestamps came in after the fact. So it's so if you implement your own version of vector clock, so if you have message loss, then this would be one way of handling it. So now you want to compose these two, use both of them together. So this is the really, really fun part, the really complex part. So you have this global model. So the first step is going to be to decompose it into a CFSM. And the decomposition is pretty straightforward, where you just pay attention to the events of the individual processes, right? So I take this model and I only look at events for process 1, right? And I treat events for other processes as epsilon transitions, right? So I'm going to receive an M, and then this is going to be, I'm going to send an M, and then this is going to be an epsilon transition for process 1, because it basically says, and then something happens somewhere else, and I don't care what it is, right? But for me, locally, I transition to this other state. So using that approach, you can decompose this thing into these two CFSMs. And these two CFSMs are very compact. As you see, they're just one state each. And the reason for that is because it is the most compact global model for that example. And then the next step is to use prior work on formal methods. Luckily, I didn't have to invent this. So there's been prior work on actually model checking CFSMs, right? And so we're going to throw it at this model that we have right now to get back a counterexample for an invariant if there is one. So for example, in this guy, there is an invariant. Send of M is always followed by receive of M. And we use a model checker called MCSCM, which model checks CFSMs exactly, and so it might not terminate. So we're thinking of using spin, but that's kind of a side point. But the point is, you want to check this invariant, and you find that there's a counterexample, right? There's an execution where I can send them, and then I can receive, and then I can execute a local event, and then I terminate. And so this execution is a counterexample to that invariant, and that execution is then going to induce a refinement of this graph. So here I can I can, I can send an M and I can execute a local event, right? And so the idea is that you want to split this guy out to require that every time you send an M, you're going to receive an M, right? And so this is refinement as before in the Synoptic case. And once you have this new global model, you do this step again, right? You're going to come back with a new CFSM, model check it, and then eventually you're going to be done. And so for this example that I worked out, the Synoptic will give you exactly these two traces, that you observed. Will give you exactly this CFSM for that example. So that's the Synoptic process. It's more involved. It has much more formal methods parts in it, and it's a little trickier. I feel like we're still struggling to understand all aspects of it. But we've done some preliminary evaluation on this, and so we've simulated some protocols, give some simulated traces. We've evaluated with Voldemort DHT, which has a replication protocol inside of it. And so we selected just the messages that have to do with replication, which turns out to be really trivial, so it's perfect for a tool. And then we've done a case study with TCP, where we only looked at opening and closing handshake. The problem with CFSMs is that they, again, don't model data. So you cannot reason about sequence numbers, for example. So you cannot do the data stage of TCP. But you can do the opening and closing handshake pretty easily. And then there's been a bunch of looking at formal evaluation and usability of these models. So I'll just show you the DHT result. So Voldemort is this distributed hash tables. It basically has this very narrow interface, right? You can associate some value with a key, or you can retrieve the value for a certain key. And this is actually deployed, but it's open source, and you can download it and exercise it. So we ran Synoptic on logs generated with unit tests by Voldemort, and we just targeted the protocol messages for replication. And so this is the CFSM that you get out. It's not as pretty. I had to prettify it manually. But basically, you have these unit tests use 2 replicas on 1 client. And this replication protocol is really straightforward. You basically have kind of a right side to it and a left side. On the right-hand side, you're executing put. You're associating a value with a key. And so this guy is going to essentially execute put on this replica, wait for a reply, and then execute a put on the lower replica. And then the same thing for get. You're going to have to do the same exact path. So they kind of mirror each other. And so through inspection, we found out that this is indeed the true model for replication in Voldemort. So it's really, really simple in Voldemort. So that's why this model is feasibly, you can inspect it. And then it succinctly captures a 3-node distributed execution from Voldemort. So the contribution here are very much like in the Synoptic case, except that we add one more, which is to handle distribution, right? So how do you handle a log that's generated by multiple processes? Our answer is you want one finite state machine per process, right? And that would be one way of doing that. And in our case, we've found that it elucidates distributed protocols because this FSM, logs that have no partial order in distributed are hard. Logs that have partial order are exact, but are even more difficult because now you have to draw these things. So a more general model can help you understand these protocols better. And so it's open source, but it's not actually deployed to, but you can try it out. So before I conclude, I want to thank a bunch of people. I worked with a trio of advisors on this project and my collaborator, and a ton of students at UW, and generously funded by DARPA, Google, and NSF. So the contributions of this talk is that I think logs have a lot of potential. They have a lot of content in them. And what I attempted to do is to apply basically formal method techniques to log analysis and model inference in these 2 tools. Synoptic infers sequential models. Synoptic infers distributed models. And the idea is that you can use these to then help developers understand what goes on in their systems. So you can find out more at this URL. And thanks for your attention. Thanks for coming. Yeah.
So what do you think is the next step in this work?
I actually am excited about applying model inference to other domains, like other kinds of problems. So I think Synoptic is an interesting theoretical kind of tool. I think it's really difficult to make it scale. So I was thinking of taking the Synoptic approach and then applying it to logs that have more information. So I was telling Peter about logs that have like timing information, for example. So you could have probability on edges, but you could also have time on edges. And you could use this to actually think about performance within your system. So now I'm actually modeling an execution, but I'm also reasoning about the time that it takes between events. And I could think about, give me the path in the model that is slowest, based on the observations, right? And I could think about that for doing things like performance testing or performance analysis. So that's like an immediate low-hanging fruit that I was thinking about. I guess in general, I'm more of a systems person, and I like to apply these techniques to systems. And so I'm thinking about doing test case generation for distributed systems. That's one of my, I think that would be a great thing to go do next, because distributed systems is very difficult to test. And I haven't, and I feel like a lot of people know how to test them well. So like when people write distributed systems code, they don't test as much, but they test very specific things. And I was wondering if there's some way to leverage that intuition that developers have about their systems to generate test cases better. So they're both kind of in the software engineering domain as applications, as techniques, but the applications would be kind of in the systems domain.
Synoptic, right? Not the Synoptic.
Yeah. There's some ways of cheating with Synoptic. I also think that, I don't think model inference is applicable to all problems. So I wouldn't necessarily use model inference for test case generation. It would be nice to, but I'm not sure if it would work out.
It seems like you touched on it, but you said that one of the sort of major asks that you seem to got from people who started using this was on the visualization was actually more useful than the raw data that was underneath of it.
Right.
Have you put more thought into what you could do or what can be done to improve that side of it? It seems from a developer story as far as like bug finding, that seems most valuable.
Right. Yeah, I think a tighter integration between the model and the log would be really useful. So right now you have some kind of window that you can peer through, into the abstraction. So you have this node and you can see the log lines that are related to it. But I think you can ask more queries of the model. Like if you can actually ask a question like, why are these two nodes split out? Why can't I merge them? And then the answer would be, well, there's this invariant and it would violate this invariant. Or if I merge them, then there's path that would violate this invariant. So being able to pose questions like that, I think would be useful. Because oftentimes when you have this log, you have a very specific question. And so the question is, I think the research question is, can you interpret that question or pose it of this abstraction and get an answer? So I think that would be very helpful. To actually, so right now it's very much open-ended. You could use it for exploration. But I think building it towards a specific set of tasks would be the right thing to do.
It's a luxury to be able to just collect logs and let's go find some bugs. Usually it's like, oh my god, it's totally broken. What's happening to the system? But that's usually why people go into these sort of avenues. So yeah, being able to have more direct.
That was my initial goal. It's like just comprehension overall, because you do use logs for so many different things. So if I just give you something slightly easier to use than a large text log, it will make your life a little bit better. But I certainly don't want to build in any assumptions about what you might be interested in, which is why the abstraction that is done by the regular expressions is left completely up to the user. Yeah. So. Thanks very much.